In this video, we're going to discuss how to take definite integrals of floor functions, sometimes referred to as greatest integer functions. So we'll be solving integrals, something like, say the integral from 0 to 3 of the greatest integer of some value x with respect to x. So we're going to try and figure out how to calculate this. So in case you do not already know what the greatest integer function is, it pretty much rounds down all the integers down to the nearest integer less than or equal to it. So if you were to graph the greatest integer function, or the floor function rather, then you would have something like this. So we're going to be looking at how to find definite integrals of functions as basic as this, and also some slight variations of it as well. Alright, to start off, we're going to look at this particular example since it's fairly straightforward. So keep in mind, the greatest integer function is not a continuous function. It is discontinuous at each of the integers. It has a jump discontinuity, so the left and right hand limits don't equal. So the integral from, say, 0 to 3, or say over an interval for which it contains several different integers, or at least one, then it's technically the fundamental theorem of calculus can't necessarily be applied. So we pretty much need to truncate the domain of integration over the course of its jump discontinuities. So in this picture, we can say, let's call this integral star. So we can say that the star integral that we're interested in finding can be found by taking the integral from, say, 0 to 1 of the greatest integer of x dx, plus the integral from 1 to 2 of the greatest integer of x dx, plus the integral from 2 to 3 of the greatest integer of x dx. So if we look at this picture, then we're pretty much calculating this area here. So in a sense, it's the area of 3 rectangles, or technically 2 rectangles in an area that's 0. So we know that the greatest integer function between 0 and 1, not including the boundaries, is just equal to 1. And we know the greatest integer function of x, if x is between 1 and 2, is just equal to, well, that's equal to 0, sorry. This is equal to 1. And we know that the greatest integer function of a number between 2 and 3, not inclusive of the boundaries, is going to be 2 as well. So we have the integral from 2 to 3 of 2 dx. So this integral is very straightforward to evaluate. So we can say that star is going to be equal to, so the integral of 0 is just 0 regardless of the boundaries, plus, so that's going to be the integral from 1 to 2 of 1, so that's going to be x, evaluated from 1 to 2, plus, and that's going to be 1, and then 2 times x, evaluated from 2 to 3. So this is a very straightforward integral to evaluate. So we have 0 plus 1 times 2 minus 1 plus 2 times 3 minus 2. 2 minus 1 and 3 minus 2 are both equal to 1. So this is just equal to 0 plus 1 plus 2, which is equal to 3. So therefore, we can say that the integral from 0 to 3 of the greatest integer function of x is equal to 3. And if you want to extend this, or make a little theorem about this, say from 0 to n of the greatest integer function, I'll leave that as a fairly simple exercise for you to try on your own. So before we look at our next example, let us just briefly recall. So side note. So the greatest integer function or operator always maps the set of real numbers to the set of integers, regardless of star, or regardless of the thing we're operating on. So whether it be x, x squared, x cubed, the square root of x, the output of the greatest integer function is always going to be an integer. So with this in mind, let's consider the second example. So say the integral from 0 to 2 of the greatest integer of x squared dx. So we already know what x squared looks like. So x squared looks like this. So this is y is equal to x squared. And what do we know? So if we take any number, say less than 1, all these range values up to this point here are going to be rounded down to 0. If we take any point to 2, so all the numbers between 1 and 2 are going to be rounded down to 1, and so on. So where do we want to go? So we want to go from 0 to 2. So when does this function x squared equal to 1? So that's going to occur at the square root of 1. When does this function equal to 2? So that's going to occur at the square root of 2. So that means we need to continue onwards. So once we hit 3, so this point here, so all these numbers between 2 and 3 are going to round down to 2. And that occurs at square root of 3. And then once we hit the square root of 4, which we know is 2, which is the upper limit of our integration, that's when the function is equal to 4. So that's going to be, so it's going to be something like this. Yeah. Hopefully you get the point. Yeah, something like that. There we go. All right, so what do we have? So we can integrate this function from 0 to 2 by breaking it up into 4 integrals. So this is 0 to square root of 1, square root of 1 to 2, square root of 2 to 3, and square root of 3 to 4. So I'm going to call this integral star again. So star is going to be equal to the integral from the square root of 0 to the square root of 1, plus the integral from the square root of 1 to the square root of 2, plus the integral from the square root of 2 to the square root of 3, plus the integral from the square root of 3 to the square root of 4. All of this of the greatest integer function of x squared dx. All right, so what do we know? So let's break it apart. Let's look at the first integral of interest. So the integral, so when x is between 0 and 1, the integral is going, the greatest integer function of x squared is going to be 0. So it's the integral of square root of 0 to square root of 1 of 0 dx. So when x is between square root of 1 and square root of 2, when you square these numbers, that's a number between 1 and 2, and all those numbers are going to round down to 1. So let's consider the numbers between square root of 2 and square root of 3 now. So when you pick a number between square root of 2 and square root of 3, when you square it, you're going to get a number between 2 and 3. So any number non-inclusive of 3 is going to round down to 2. So this is going to be 2. And any number from square root of 3 to the square root of 4, which of course is equal to 2, is going to round down to 3, non-inclusive of the boundaries, of course. All right, so once we get to here, then everything should be fairly straightforward. So the first integral is going to be 0. So 0 times the square root of 1 minus the square root of 0, plus 1 times the square root of 2 minus the square root of 1, plus 2 times the square root of 3 minus the square root of 2, plus 3 times the square root of 4 minus the square root of 3. And you can start to see a pattern for which you could bring together to pretty much generalize a more stronger identity for this. So what do we have? So that's going to be equal to 0, no big deal there. So we have a square root of 2 minus, well, the square root of 1 is just 1. Then we have 2 square roots of 3's minus 2 square roots of 2's. And then we have 3 times 2, which is going to be 6, minus 3 square roots of 3. And then it can combine like radicals. So we have our root 2's there, our root 3's here, and our integers there. So once we combine, what do we have? So we have 6 minus 1, which is 5. Let's do our root 2's next. So root 2 minus 2 root 2 is going to be minus root 2. And then 2 root 3 minus 3 root 3 is going to be minus root 3. So that means what? So that means our star integral, the integral from 0 to 2 of the greatest integer of x squared with respect to x, is going to be equal to 5 minus root 2 minus root 3. So that's our final answer. So there are definitely some identities for which we can start to build here. The first main theorem that you should be able to prove is the following results, and that is this. So the integral from k to k plus 1 of the greatest integer of x dx is precisely equal to the lower bound k. So this is the first theorem that should be very easy to prove via the examples above to sort of guide you through that derivation. So with this in mind, let's do a third example. Suppose we want to find the integral from 0 to 5 of the greatest integer of x cubed dx. So what we're going to do is we're going to perform integration by substitution to sort of bring together some of the other methods that we've used in the past. So I'm going to let u be equal to x cubed, forcing du to be equal to 3x squared dx, which forces dx to be equal to du divided by 3x squared. So this is the first statement. Secondly, so when x belongs to the interval 0 to 5, we know this is going to force u to belong to the interval 0 cubed comma 5 cubed, which is of course the interval 0 to 125. So that's our second piece of information. Also, we need to know what x squared is in terms of u. So if u is equal to x cubed, what we can do is we can, let's do a 2/3 power to both sides. So this is going to force x squared to be equal to u to the 2/3. So that's going to be applied to our differential of x term. So with all these things in mind, I'm going to call this star. So star is going to be equal to the integral from 0 to 125 in terms of u, and then we have the greatest integer of u times our differential of x, which is du divided by 3 times x squared, which is u to the 2/3. Alright, so what do we have? So star, in this case so far, is going to be equal to 1/3 times the integral from 0 to 125 of the greatest integer of u over u to the 2/3 du. So what I'm going to do is I'm going to apply that property from before, and I'm going to break this function up at all of the jump discontinuity parts, because we know u to the 2/3 is continuous for all values u. And also the greatest integer of 0 is 0, and u to the 2/3 at 0 is 0. So this 0 over 0 is a removable discontinuity, so the singularity actually does not pose any issues, so it still converges. So we're going to break this apart on intervals from 0 to 125, so we're going to go from 0 to 1, 1 to 2, 2 to 3, 2 to 4, 3 to 4, all the way up to 124 to 125. So once I do that, what do I have? So I'm going to have, this is 1/3 times the sum from k is equal to 0 to 124, so 1 less than the upper limit, of the integral from k to k plus 1 of the greatest integer of u, u to the 2/3 du. And now I can use that property that this is precisely equal to k on each of these subintervals. So we have that star is equal to 1/3 times the sum from k is equal to 0 to 124 of k times the integral from k to k plus 1 of u to the minus 2/3 du. And this integral is a little bit more friendlier to deal with. So we're going to apply the fundamental theorem of calculus on u to the negative 2/3 because, because we can. So once we do that, what do we have? So we have that star is equal to 1/3 times the sum from k is equal to 0 to 124 of k times, so add 1 to that, that's going to be u to the positive 1/3, all divided by the reciprocal of 1/3. And then we're going to evaluate this as u goes to k plus 1 and as u goes to k. And once we have this, we have star is equal to, so they cancel, and we have the sum from k is equal to 0 to 124 of k times the cube root of k plus 1 minus the cube root of k. Now, there's no short identity that you can use for this, so you can pretty much leave this as your exact answer, or you can find the approximation of it to be 154.03, or you can treat that as the exact answer. So what we've done in this video is pretty much discussed a couple strategies in order to evaluate definite integrals of greatest integer functions and also some variants of it as well. Hope you enjoyed.